Hello Bobcats. Today we're going to do some electron configuration and orbital diagram practice. So I have a blank periodic table here. We have the energy levels or periods of 1, 2, 3, 4, 5, 6, 7. And then I've indicated the S block, the P block, the D block, and the F block represented in each of the separate sublevels of an atom. So first let's take phosphorus. Now phosphorus is found right here. So there's phosphorus. And the way I would work on it is I would write the electron configuration first. And so the electron configuration for phosphorus, I can start out, of course I'd write the element to indicate what I'm doing. And then we know that the energy level 1 and energy level 2 are completely filled because phosphorus is on energy level 3. So I can go up and over and use the noble gas right here, neon, to indicate that the first 10 electrons are in filled energy levels. So I can go neon, this is called the noble gas notation for electron configuration. So I would do neon, and then I would start, and I'd have 3, and then using the each block to count an electron, I'd have 3s, 1, 2, and then go over 3p, 1, 2, 3. So I'd say 3s, 2, 3p, 3. And when I look at this, I notice that on the outer energy level, the third energy level, I have 2 plus 3, 5 electrons. So that's 5 valence electrons for phosphorus. Now the orbital diagram can be written done in the same way in which I'm going to indicate the element, then I'm going to use neon to represent the first 10 electrons in the filled energy levels above energy level 3. And then I'm going to show orbitals. So S has 1 orbital, and then P has 1, 2, 3 orbitals. So that's the 3s and the 3p orbitals. And again, we have 2 in the S sublevel. So when I look at this, Pauli exclusion principle says that you can only fit 2 electrons in each orbital if they are in opposite spin. And the maximum you can fit in each orbital is 2 electrons. So I have an electron of 1 spin and then an electron of the opposite spin. So I filled the S sublevel, and now I move up to the P sublevel with the P orbitals. And there's 3 electrons. So the next thing is that we follow Hund's rule in that if you have orbitals in the same energy, then you put an electron in each orbital before you double up. So I have 1, 2, 3 electrons. And this shows the 5 valence electrons in the outer energy level. So let's choose another one. It's a little bit different. Let's try nickel, and we can find nickel right here in I, nickel. So again, I'm going to start with the element, so you know what I'm looking at. And nickel, if I go up and over, we know that these 3 levels up here are completely filled. So I go up and over, and this noble gas, which has 18 electrons, will represent the filled energy levels of those 18 electrons. So we have argon, and then I start over here again, and I have 4s, 1, 2. So I write 4s, 2. And now remember, we start at a lower energy level with D, so it's 3D. Now the reason is, remember, the octet rule states that the maximum amount of electrons in the outer energy level can be 8, and those 8 come from the S and P orbitals. So D has to be one energy level lower than the S and P when it is being used. So we have 3D, and then I count 1, 2, 3, 4, 5, 6, 7, 8. 3D, 8. Now, nickel has a atomic number of 28. Let me grab my periodic table. I should have had one ready, but I didn't. when we look here, nickel is number 28, and so I can count and make sure that I did this correctly, count the electrons. So I have 18 plus 2 is 20 plus 8 is 28 electrons. Now I'm going to do the orbital diagram. So I have nickel. We're going to start with argon, and I've got the 4s, and then D has 5 orbitals, so that's 1, 2, 3, 4, 5. So it's the 4s, 3 D orbitals. Again, we put the first 2 electrons in the s with opposite spins, and then we put an electron in each orbital first before we go back and double up. So I have to put in 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. And so that's my orbital diagram for this electron configuration for nickel. Let's choose one more, and then we're going to talk about the exceptions that can occur. So if I do 10, this is 10 SN. Oh, let's pick a different color. So I'm going to do 10. I'll do it in green, SN. So start with 10. Now I'm going to go up and over to the end over here. So when I look at my periodic table, 10 goes up and over. I'm going to use krypton to show the energy levels that are filled above where 10 is. So that's krypton, which accounts for 36 electrons. And then I start over again. I have, is 10 in the 4th or 5th? 1, 2, 3, 4, 5th. Okay. So here I go. I'm going to start, and I've got 5s1, 2. Then 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 4d, 10. And then I have 5p1, 2. 5p2. Now, sometimes you will see it written in a slightly different order, and it's okay to do this. I just like to do it the way I see it on the periodic table. But a lot of books will like to do it where you do the lower energy first, so 4d10, and then 5s2, 5p2. So that's 4 valence electrons. So you can see the valence electrons right away when you see these in the 5th energy level. Now the orbital diagram will look like we have 10. We're going to start out with krypton. And we have 1 orbital for the s, 1, 2, 3, 4, 5 for the d, and then 1, 2, 3 for the p. So that's 4s2, 3d, 4s, 3d, and then 5s, 4d, 5p. Sorry about that. 5, it's 5s, 4d, 5p. And I put my electrons in. I have 2 in the s, so that's 1, 2, 10 in the d, so 1, 2, 3, 4, 5, 6, 8, 9, 10, and then 2 in the p, 1, 2. And that would be your orbital diagram for 10. Now let's briefly discuss the exceptions. So I'm going to look at exceptions here. And the first one we're going to look at is chromium. And chromium is found right here. And so if we do the electron configuration, or let's do the orbital diagram. It'll help us out understand why the exception occurs. So we're going to do the orbital diagram first. So if I look at chromium and I go up and I go over, that's argon. So chromium is going to be argon, and then we go 4s2 3d 1 2 3 4. So you would think that we'd write 4s2, oops, I'm actually doing electron configuration first, apologize, 4s2 3d4, but this is incorrect because this is the exception, and let's see why this, or what happens here. So when I do my orbital diagram, sorry, I did electron configuration first, then I'm going to do orbital diagram. So I have argon, and then we have the 4s, and then the 3d, 3, 4, 5. So 1, 2, and then 1, 2, 3, 4. Now what we have here is, you notice that there's an empty orbital over here, and atoms like to have some orbital stability. This is up here. If I look at phosphorus, these with a half-filled sublevel create some stability because it's half-filled. And so in order to gain some of that stability, what happens is this electron will then be transferred to that orbital, and you'll get chromium, and that's 4s 3d 1 2 3 4 5, and then you'll have an electron in the 4s, and then 1 2 3 4 5 electrons in the 3d. And so now I have some orbital stability by half filling that third sublevel, or putting an electron in each of the orbitals in that third sublevel, the d sublevel. And so this is incorrectly written, and the way I would do it correctly is chromium with argon, and that would be 4s1 3d. I said 10 up here and I meant 4 here. Dang it. I'm making quite a few mistakes. I may have to redo this video. Anyway, so there's 4s1 3d5. And so you'll notice that that will also happen with copper, because copper has 1 2 3 4 5 6 7 8 9 electrons in it. And so to completely fill the d sublevel, to have stability, it will take an electron from the 4s and put it in the other one and have 10 electrons in the 3d and 1 electron in the 4s. And I hope that is helpful for you guys. Thank you very much.